System boot and self-diagnosis, 0.2 seconds. The vehicle awakens as primary and backup computers power on simultaneously. A rigorous self-check scans all 40-plus sensors, 12-plus processors, brake-by-wire systems, steering actuators, and communication modules. Any critical fault, like a malfunctioning forward radar, prevents engagement. The car establishes a secure connection to its fleet network, downloading the latest map updates and traffic reports. High-definition localization, 0.1 seconds. Using GPS, accurate to 10 centimeters with ground-based correction. Inertial measurement units, wheel encoders, and by matching live camera images to stored 3D maps, the car determines its exact position within a 5-centimeter radius. It knows not just, I'm on Main Street, but, I'm 3.2 meters from the northwest curb, aligned at 12.7 degrees relative to my lane center. Pre-drive scenario loading, 0.3 seconds. The system loads a hyper-detailed 3D map of the immediate 500-meter radius. This isn't a navigation map. It's a centimeter-accurate blueprint containing lane widths, curb heights, traffic sign placements, pothole locations, permitted turning paths at intersections, and even historical pedestrian crossing hotspots. This serves as its prior knowledge of the static world. LiDAR spatial sculpting, 0.05 seconds per cycle. The rooftop and bumper-mounted LiDAR units emit 1.2 million laser pulses per second. Each returning photon's time of flight is measured, generating a real-time, rotating 3D point cloud. A ghostly digital twin of the physical environment where every tree branch, car contour, and fire hydrant is represented as a cluster of precise points in space. Radar's velocity penetration, 0.05 seconds per cycle. 7 radar sensors, operating at different frequencies, send out radio waves. By measuring frequency shifts in returning signals, Doppler effect, they detect not just objects but their precise radial velocity. A rear corner radar might report object at 45-degree angle, 8.2 meters away, approaching left side at 2.3 meters per second. Radar sees through rain and fog where cameras go blind. Computer vision's labeling, 0.07 seconds per cycle. 8 high dynamic range cameras, with overlapping 360-degree coverage, feed images into deep neural networks trained on millions of labeled images. These networks identify and classify, not just vehicle, but sedan, emergency vehicle, school bus, not just human, but pedestrian facing away, cyclist with arm extended, construction worker holding stop sign. Ultrasonic proximity sensing, 0.02 seconds per cycle. 12 ultrasonic sensors fill the immediate bubble, 0 to 5 meters, with high-frequency sound waves, creating a tactile proximity map perfect for detecting a child's toy near a tire or precisely measuring distance to a garage wall during parking maneuvers. Sensor fusion, creating the unified scene, 0.1 seconds. This is the car's most critical cognitive act. A central fusion engine takes LiDAR's precise 3D shape of a moving object, radar's confirmation that it's moving at 12 miles per hour, camera's classification that it's a bicycle, historical data that this stretch has bike lanes. It fuses these into a single tracked entity. Bicycle_01, trajectory 23 degrees, speed 5.4 meters per second, 95% confidence, currently in bike lane. The car now maintains a dynamic list of 200+ such tracked objects, each with properties and predicted behavior. Intent prediction through behavioral models. For each dynamic agent, the system runs multiple prediction models. Physics-based, assuming current velocity continues. Map-based, predicting a car will follow lane curvature. Interaction-aware, noting that a pedestrian's head is turned toward the road, 70% chance of crossing. Learning-based, using neural networks trained on thousands of hours of driving data to recognize subtle cues. A shopping cart angled toward the street, a delivery truck's brake lights while double parked. Traffic law interpretation. The AI cross-references its unified scene with known regulations. It doesn't just see a red light, it understands. California Vehicle Code 21453, a stop required at marked limit line. Right turn permitted after complete stop if no pedestrians and sign allows. It evaluates conflicting information, a police officer's wave versus a red light, and follows hierarchy of authority. Occlusion reasoning. The car actively models what it cannot see. A parked delivery truck obscures the sidewalk. The system creates a risk volume behind it, anticipating a possible pedestrian emerging. It might slightly shift position to get a better sight line, just as a human driver would. Mission planning, 30-second horizon. Based on the destination, the routing system selects the optimal path considering real-time traffic, road closures, and even energy efficiency. Take highway for 3 miles, then exit at Oak Street, then residential streets to destination. Behavioral planning, 10-second horizon. This layer decides maneuvers. Change lanes left to pass slower vehicle, then prepare for upcoming right turn by moving to right lane. It sequences high-level actions. Motion planning, generating candidate trajectories, 0.5 seconds. The system generates dozens of possible paths the car could follow in the next 5 seconds, each a smooth curve in space-time. One might stay centered in lane, another might shift slightly left for buffer from a cyclist, a third might prepare for gentle braking. Cost function evaluation, the value system. Each trajectory is scored by a complex cost function that balances safety, highest weight distance to obstacles, time to collision; legality, staying in lane, obeying speed limits; ride comfort, jerk, rate of acceleration change, lateral g-forces; efficiency, progress toward goal, energy consumption; social norms, predictability to other drivers, not being overly cautious. A trajectory that brakes too hard gets penalized for discomfort. One that passes too close to a cyclist gets an extremely high cost, effectively vetoing it. Optimal trajectory selection. The system selects the lowest cost feasible trajectory. This isn't necessarily the shortest or fastest, it's the best balance of all values. The chosen path might be: gently decelerate at 0.2 g to maintain 3-second following distance from car ahead, while maintaining 1.2 meter buffer from parked cars on right. Trajectory decomposition. The smooth mathematical curve is broken down into a time series of commands. At t equals 0, steering angle 2.1 degrees, acceleration 0.8 meters per square second. At t equals 0.1 s, steering angle 2.0 degrees, acceleration 0.79 meters per square second. Precise actuator control. Commands reach redundant drive-by-wire systems. Steering. Electric power steering motors receive 1000 updates per second. Throttle. Electronic throttle control modulates torque precisely. Brakes. Electro-hydraulic brakes apply pressure to individual wheels, capable of anti-lock and stability control interventions. Real-time closed-loop correction. As the car moves, it constantly compares its actual position from sensors with its planned trajectory. Minor errors, wind gust, road unevenness, are corrected 100 times per second through micro-adjustments, creating a smooth ride despite imperfect reality. V2X integration, if equipped. The car receives vehicle-to-everything messages. From traffic lights, red for 4.2 more seconds. From emergency vehicles, ambulance approaching intersection from east. From road infrastructure, black ice detected 200 m ahead. From other connected vehicles, hard braking event 2 cars ahead, creating electronic sight through obstacles. System health monitoring. While driving, the car continuously validates its own perception. If camera and LiDAR disagree substantially about an object's distance, the system might downgrade confidence in that sensor, rely more on others, or initiate a cautious slowdown. Redundant computers constantly check each other's calculations. Human-machine interface management. If a human is present, interior cameras and sensors monitor head position and gaze direction. Is the passenger watching the road? Hand position on/around steering wheel. Verbal cues indicating intent to take control. The system prepares appropriate alerts or handover procedures based on this assessment. Failure response planning. Every 0.1 seconds, the system evaluates. If my primary trajectory becomes blocked right now, what's my fallback? This might be moving to the shoulder, stopping in lane, or executing a minimum risk maneuver to a predetermined, safe harbor location. Fleet learning upload preparation. When the car encounters a rare or challenging scenario, an unusual construction zone, an ambiguous traffic agent behavior, relevant sensor data and the car's response are anonymized and queued for upload. This data will help improve the neural networks for the entire fleet. The cycle resets, perpetual awareness. The entire process, from sensor fusion to trajectory execution, restarts. Not from scratch, but building upon the previous cycle's world model. This loop runs continuously at 10 Hz, 10 times per second, for the behavioral layer, and up to 100 Hz for the control layer, creating a river of perception, prediction, and action that only ceases when the vehicle is fully powered down. The final insight: this isn't a linear 25-step checklist, but a symphony of parallel processes, some running 100 times per second, others every few seconds, all harmonized to create the illusion of seamless, intelligent driving. The car's thinking is this constant, dynamic dance between perceiving a changing world, imagining possible futures, and selecting actions that navigate toward the safest, most lawful, and most efficient outcome.